Previously, we covered the core foundations. Now, in part 2, we tackle Earth, atmosphere, and oceans. In the last episode, we looked at Earth as a world, its size, its orbit, its place in the solar system. But size and distance only tell you so much. What actually makes this planet livable is something far thinner and far stranger than the rock beneath your feet. Earth carries a shell of gas and a skin of liquid water that together do something no other planet in the solar system manages. They keep the surface warm enough, stable enough, and chemically active enough to sustain complex life. The core question for this episode is straightforward. How do the atmosphere and oceans actually work as a system? And what does Earth look like when you compare it honestly to its neighbors? That comparison matters because understanding what we have requires understanding what we nearly didn't. Section 1. The atmosphere, structure, and composition. Let's start with the atmosphere itself. From the ground, the sky looks limitless. It isn't. The atmosphere has a total mass of roughly 5.1 times 10 to the power of 18 kilograms, which sounds enormous, but spread across the entire surface of the Earth. That translates to an average pressure of about 1 bar at sea level, roughly the weight of a 1 kilogram mass pressing down on every square centimeter of your skin. You don't feel it because your body pushes back equally in all directions, but it's there, constantly. The atmosphere is divided into layers, each defined by how temperature changes with altitude. The troposphere is the lowest, the one we live in. It extends from the surface up to roughly 12 kilometers at mid-latitudes, though it's somewhat thicker at the equator and thinner at the poles. Almost all weather happens here. Temperature drops as you climb at roughly 6.5 degrees Celsius per kilometer on average. Above that sits the stratosphere, reaching up to about 50 kilometers. Here, temperature actually increases with altitude, because ozone in this layer absorbs ultraviolet radiation from the sun. That reversal of the temperature gradient is what gives the stratosphere its name. It stratifies, meaning it doesn't mix much with the layers around it. Without the ozone layer sitting within it, ultraviolet radiation at the surface would be intense enough to disrupt DNA in most surface life. Above the stratosphere, the mesosphere, then the thermosphere, then the exosphere, where individual molecules can escape into space entirely. Beyond 100 kilometers, by convention, you're in space. That's the Kármán line. Now, composition. Earth's atmosphere is roughly 78% nitrogen and 21% oxygen, with the remaining 1% dominated by argon and a small but critically important trace of carbon dioxide, currently just over 400 parts per million. Water vapor, methane, nitrous oxide, and other gases make up the rest in trace amounts. That nitrogen-oxygen mix is unusual in the solar system. Venus has a dense carbon dioxide atmosphere. Mars has a thin one, also mostly carbon dioxide. Jupiter and Saturn are hydrogen and helium. Earth's oxygen-rich air is almost entirely a biological product, the result of billions of years of photosynthesis pumping oxygen into a world that originally had very little of it. Which raises a question worth holding on to. How did we get from a reducing, oxygen-poor early atmosphere to this one? We'll come back to that. Section 2. The greenhouse effect and temperature regulation. Earth's average surface temperature is roughly 14 degrees Celsius. Strip away the atmosphere entirely, and the planet would radiate heat into space so efficiently that the average surface temperature would drop to around minus 18 degrees. That's a difference of about 32 degrees, and that difference is the greenhouse effect. The mechanism is straightforward. Sunlight passes through the atmosphere and warms the surface. The surface then radiates that energy back as infrared radiation. Greenhouse gases, primarily water vapor, carbon dioxide, and methane, absorb that outgoing infrared radiation and re-emit it in all directions, including back towards the surface. This slows the rate at which heat escapes, and the surface ends up warmer than it would otherwise be. None of this is new or controversial. The basic mechanism has been understood since the mid-19th century, when the Irish physicist John Tyndall demonstrated experimentally in 1859 that carbon dioxide and water vapor absorb infrared radiation. The Swedish scientist Svante Arrhenius calculated in 1896 that doubling atmospheric carbon dioxide would raise global surface temperatures by several degrees. The comparative picture is dramatic. Venus is roughly the same size as Earth and sits somewhat closer to the Sun. Yet its surface temperature averages around 465 degrees Celsius, hotter than Mercury, which is far closer to the Sun. The reason is Venus's atmosphere, 90 times denser than Earth's, composed almost entirely of carbon dioxide, with thick sulfuric acid clouds, an extreme greenhouse effect, essentially unchecked. Mars went the other way. Its thin atmosphere holds very little heat. Surface temperatures average around -60 degrees Celsius, with extreme variation. Mars lost most of its early atmosphere, partly through solar wind stripping, partly because without a strong magnetic field, there was little protection, and partly through the planet cooling and losing the volcanic activity that would have replenished what escaped. Earth sits in what's sometimes called the habitable zone, the range of distances from a star where liquid water can exist on a surface at reasonable pressures. But habitability isn't purely about distance. It's about the balance of the whole system. Section 3. The oceans. Now for the open loop from earlier. The shift from an early, reducing atmosphere to the oxygen-rich one we have now. The oceans are central to that story. Earth's oceans cover approximately 71% of the surface and hold about 1.3 billion cubic kilometers of water. Average depth is around 3,700 meters. At the deepest point, Challenger deep in the Mariana Trench, the ocean floor sits nearly 11 kilometers below the surface. The oceans are not just water. They're a global heat engine, a chemical system, a biological habitat, and a critical part of the carbon cycle. As a heat engine, water has an exceptionally high specific heat capacity, meaning it takes a lot of energy to raise its temperature, and releases that energy slowly as it cools. Subscribe so you do not miss it.